Hey, you guys. This is Kaylee again. So, as you may notice, you are not sitting in class right now. If you are, please go home. I'm not going to come. So, today we're going to be talking about Chapter 6, which is going to be our confidence intervals. And so, as a reminder, the quiz does go over section 5.5, so make sure you go back and study that section again for the quiz. I did go over an example problem in my previous review, so if you want to go take a look at that, go ahead and do that. It's really similar to the rest of Chapter 5, you're just going to have some new equations. So, and again, we're not having class on Friday / today / whenever you're watching this video, so enjoy your spring break. So first of all, let's talk about what a confidence interval is. A confidence interval is going to measure an expected mean when we're using sample data to calculate a proportion mean. The confidence interval includes a range in which the mean will lie. For example, if we're talking about the mean number of cats in each household in Cedar City, it could be 0 to 3. It essentially gives us an estimate for the mean. Remember back in chapter 5.5 when we were doing point estimates for the mean, where the sample mean was equal to the population mean, given that we had a representative sample. But here we're adding more nuance, saying, well, there actually could be a range for the population mean because even though a sample is representative, it's not necessarily perfect. And so we're just adding more nuance to our statistics that we're calculating. So when we're calculating our estimate, we're essentially exchanging accuracy and precision by using the different confidence levels. For example, in a 99% confidence interval, the probability that our mean will lie between those two numbers is 99%. But with the lower confidence level, we would have a probability of 90% that our mean would lie between the two numbers. There is a catch though. The 90% confidence interval is going to have a smaller gap between the number estimate. For example, if we're going back to our cat problem, a 99% confidence interval would be, for example, from 0 to 3, and a 90% confidence interval would be from 1 to 2, where the 99% confidence interval gives us a larger range where we're more likely to find our mean between those two numbers, where the 90% confidence interval is more specific, but there is a chance that the mean could lie outside of that. So which one is the better one to use? It just depends on what your goal is. If you just want the mean included in your confidence interval, you're going to use the 99% confidence interval. If you care about having a small range for your mean, just go ahead and use the 95 or the 90% confidence interval. Thankfully, all of our confidence intervals will be given to us, so we don't have to worry about that. So the next most important thing to do is to know how to calculate the error E. And so the error is how we're going to create the confidence interval, essentially by taking our point estimate and then we're going to add and subtract error to create the two sides of our interval. And so that's essentially how you create the confidence interval. For our terms and definitions, we have a critical value that's going to be assigned to each distribution that relates to our confidence level. For example, if we have our ZC and our negative ZC, where ZC is taken from our confidence level, like for example a 99% confidence level, and then we're going to take that area under the curve, and then we're going to figure out where that z-score lies to give us our critical value. The margin of error is going to be the greatest distance between the point estimate, which would be x bar, and the value of the parameter, which would be mu. And you can replace x bar and mu with each respective symbol like p, p hat, etc. And then c, which is the confidence level, which is the probability that the confidence interval contains the parameter we're trying to figure out. So to construct our confidence interval, like I said before, we're going to take our point estimate x bar and we're going to subtract our error, and then it's going to be less than mu, which is less than x bar, and then adding the confidence level again. And so that's how our confidence intervals are always going to look, and so you don't have to worry about that too much. It's going to be the same for each of them. To calculate our error, specifically for when we're calculating the mean, where we have the standard deviation, what we're going to do is we're going to take our ZC, which is our critical value, we're going to multiply it by sigma, which is the population standard deviation, and divide by the square root of n. And so you can use the table in your book to find the critical values for each confidence interval, but I just went ahead and copied them here, where you have the 99% is equal to that, whatnot. And so those are the only confidence levels we'll be using. So jump into our first example. Let's go ahead and take a look at question number 52 in section 6.1. So this is a juice dispensing machine. A beverage company uses a machine to fill half-gallon bottles with fruit juice, and the company wants to estimate the mean volume of water the machine is putting in the bottle within 0.25 fluid ounces. So what is the minimum sample size required to construct a 95% confidence interval when the population standard deviation is 1 fluid ounce? And so I'm going to hop back to part B in a minute, but let's go ahead and do part A first. So first things first, I'm a realist. Page 304 has the equation that we're going to use to calculate the minimum sample size, where n equals your critical value times the population standard deviation divided by your error, and then all of that is going to be squared. And so I went ahead and then I found the confidence level, which was 95%, and so I went back to our little table here, and I found the confidence level, which is I found the critical value, which is 1.96. And so going back there, I went ahead and copied that. And then for the standard deviation, we are given that it's 1. And then for the error, it's going to be 0.25, which it explained up at the beginning, where we want to estimate the mean volume of water within 0.25 fluid ounces. It's giving us the error it wants to construct the confidence interval within. And so we went ahead and copied that. To calculate our n, let's go ahead and put in our numbers. We're going to go ahead and do our ZC and multiply that by our population standard deviation divided by our error and squared. I'm just going to go ahead and click out of that and then make it so you can see that. Let's look at that again. There we go. Where we had ZC times the sigma divided by error squared. Okay. Now hopping back to part 2. We're given now that the sample mean is exactly 64 fluid ounces, with a sample size of 68 and a 95% confidence level and a population standard deviation of 1 fluid ounce. Does it seem possible that the population mean could be greater than 63.85 fluid ounces? And explain your answer. For this one, I went ahead and copied down the information that we've been given. Our x bar, or the mean, is 64, the n is 68, and then our critical value is still 95. Our confidence level is still 95% as it was before. So I went ahead and copied that critical value down. Oh, I'm about to sneeze. Okay, and then the standard deviation came out to 1 again. Next, we're going to calculate our error, since the error 0.25. We don't know if it's true anymore, since now that we've been given our x bar and our n, it could fluctuate. So to calculate that error, let's go ahead and make that formula visible. We're going to take our we're going to take our critical value, and then we're going to multiply it by our standard deviation divided by the square root of n, where the standard deviation divided by the square root of n is in its own function. And then it's all multiplied by the critical value. And that gives us our error of 0.23. Next, to calculate the left end and the right end, we're just going to go ahead and do the mean, and then we're going to subtract the error right there. And then we'll do the mean and we'll add the error. Okay? That gives us our left end and our right end. Next, to put that into confidence interval notation, we're going to go ahead and say that 63.76 is less than mu, which is less than 64.24. And then next for our explanation, we're going to try to figure out whether or not the mean could be greater than 63.85. So 63.85 is included inside of our confidence interval, and so is values that are greater than 63.85. Therefore, it is possible that our population mean could be greater than 63.85, and we have a 95% probability of that being the case. Yeah, that's for section 6.1. Next, for section 6.2, we move into calculating the population mean and the interval without the standard deviation, without the population standard deviation specifically. For this one, we're going to be using a new distribution called the t distribution. It's essentially the exact same as the normal distribution, but instead the standard deviation is going to be smaller and is going to be based off of the degrees of freedom in the problem, where the degrees of freedom equals n minus 1. In our t distribution table, the confidence level will be at the top and the degrees of freedom will be on the left-hand side as shown here. This is just a photo I stole off the internet. Love it. Okay, and then we have some new equations that I would recommend taking a look at. For your t, you're going to do your x bar minus mu divided by s divided by square root of n. Your x bar and the sample standard deviation are still going to be the same way that we calculated them previously in chapter 1. And so we can still use the equals average and the equals stdv.s, and then you'll be all good to go. Next, for our formula for error, we're going to have our t critical value, and then we're going to multiply that by our sample standard deviation divided by the square root of n. And then remember that for the sample standard deviation, that's represented by lowercase s, and the population standard deviation is represented by sigma. So remember that when you're looking for the difference between s and sigma, just remember which values they correspond to, the population or the sample distribution, or the sample value, sorry. Okay, so for our next section, I have two examples for you. So question 18 and 6.2, we are given the sample mean and the sample standard deviation, and we're going to assume that the population is normally distributed, then use the t distribution to find the margin of error and construct a 95% confidence interval for the mean, then interpret our results. So for this question, we have a random sample of 5 people where the mean driving distance to work was 22.2 miles and the standard deviation was 5.8 miles, and that was a sample standard deviation that was given to us. So I went ahead and copied that information down where our x bar is 22.2, the sample standard deviation is 5.8, our n is 5, and then our degrees of freedom is going to be n minus 1, which is that 4 right there. Next, I'm going to go ahead and figure out what our critical value t is, and so I'm going to go ahead and take our degrees of freedom, which is 4, and then we're going to find our 95% confidence interval. So going back to this previous page, let's go ahead and look at for a 95% confidence, and then we're going to match it with the 13 right there for our degrees of freedom. That gives us a value of 2.160. Oh, did I do that wrong? Oh, wow. I said 13. The degrees of freedom is 4. That's why I always want to double check. There we go. Let's try that again. There we go. With our degrees of freedom being 4, the correct degrees of freedom, our new value for the critical value is going to be 2.776. So given our value of 2.776, we're going to go ahead and calculate our error. Let me go ahead and make that visible for y'all. So our error is going to be our critical value multiplied by the sample standard deviation divided by the square root of n, which gives us a value of 7.25. For the left end, let me go ahead and make that visible for you, and then the right end. So for the left end, we're going to go ahead and take our mean, our mean and subtract the error, and then for our right tail, we're going to take the mean and add the error again to give us our two sides. And then to create our confidence interval, we're going to go ahead and do the left end to the right end, and then I always make sure to round it to 2 places. And so when we round up the 14.9995, we just need to make sure we include the 2 decimals, the 15.00, to represent that, yes, we did actually round it correctly. And then we're going to go ahead and add that right tail, 29.40. Okay, and then for our explanation, let's go ahead and make that visible. There's a 95% probability that the mean driving distance lies between 15 miles and 29.4 miles. For question 26, we're going to construct a 99% confidence interval for the mean, calculate the sample mean and the standard deviation, and assume that our population is going to be normally distributed. For this one, we're given various GPAs of 14 randomly selected students. I already took the liberty of copying and pasting the values here, so just take a moment to pause if you need to add those. For our mean, we're just going to go ahead and use our average function in Excel, which is equals average. And then the same thing for our standard deviation. Just make sure you do equals stdv.s, not the stdv.p. Otherwise, we'll use the wrong equation. So make sure that you remember that you're calculating a sample mean, not a population mean. Wow, a sample standard deviation, not a population standard deviation. So our n is 14 as they gave to us, and then our degrees of freedom is going to be 1 minus n minus 1, which is going to be 13. Our critical value, we went ahead and found it in the table where we have our degrees of freedom is 13, and then our confidence level is 99%. So if we look for our 13 degrees of freedom and then go to exactly 99%, that will give us our value of 3.012. Yep, right there. For our error, we're going to go ahead and use that same formula that we did before, where we take our critical value and multiply that by our standard deviation divided by the square root of n. And then, again, for our two sides, we'll just take the mean and subtract the error, and then mean and then add the error. And then for the confidence interval, again, we're just going to place the left-hand side between mu and the right-hand side. Right here where we have 1.8 is less than mu, which is less than 3.21. And then thankfully, that's all we have to do is construct the confidence interval, and we're done. For our proportions, it's going to be really similar to our previous section when we were doing our confidence levels for our means given the sample standard deviation. I find population proportions to be quite easy, and also the little hats on the P's and the Q's just make me happy, so there you go. So our P hat is going to be equal to x minus x divided by n again, where our Q hat is 1 minus P hat. Our error is going to be our critical value times the square root of P hat times Q hat divided by n. And we're going to remember that our NP and NQ still have to be greater than 5. For our minimum sample size, we have P hat times Q hat times our critical value divided by E squared. And so those are all the new equations that you need. Pretty simple. For our examples, for our last example we're going to do today, we're going to look at exercises 25 and 26 in section 6.3. So in these exercises, we're going to use the figure below where 1,003 adults from the US, 1,020 adults from Canada, 999 adults from France, 1,000 adults from Japan, and 1,000 adults from Australia were asked whether national identity is strongly tied to birthplace. And so we're going to construct a 99% confidence interval for the population proportion of adults who say that national identity is strongly tied to birthplace for each country. That is a lot of work. But the good news is that we have Excel that will help us out. So for our P hat, I just went ahead and copied down the values that were given on the table. If you just want to pause here for a second and copy those values down for P hat and N. Next, to calculate Q hat, what I did was I just took each P hat and I did 1 minus that. The nice thing about that is that when you calculate the value, all you have to do is drag and drop, and then Excel will autofill it for you. Brilliant. Next, to calculate RE, sorry, let me make that visible for you. We're going to go ahead and do the equation that we had previously, where we have our critical value and multiply that by the square root of P hat times Q hat divided by N. Again, to calculate that for all of the countries, I just went ahead and dragged and dropped those values. There's no need to add any permanent cell references because all of the cell references are shifting with each equation, so we're all good to go. For our left and right ends of the point, we're going to go ahead and do the same thing where we do our P hat minus E, and then our p hat plus P. Again, I drag and drop those down. For the confidence interval, we're just going to go ahead and set up those the same that we did previously. And then Excel autofilled the rest of the 5 for me. It was amazing. I was so thrilled. And so that is one of the reasons why Excel is superior to doing it by hand, because we were able to do 5 times the amount of work with 5 times less effort. It was amazing. So, for question 26, does it seem possible that any of the population proportions could be equal, and let's explain. So let's go ahead and look at our different confidence intervals. And so if any of our population proportions could be equal, essentially we're looking for overlap between the various distributions where, for example, there could be overlap between US and Japan or Australia and Canada. And so as I'm looking at these values, it doesn't look like there's any overlap between any of the values. For example, 28 is not between 17 and 24. There could potentially be a tiny bit of overlap between the U.S. and France, but in general, like they're just too far apart. Where the overlap between the U.S. and France is like 0.3%. Like that's just such a small overlap for such a large confidence interval. It doesn't make sense. And then like the 45 isn't included anywhere, nor is the 15. And so because of that, I'm just going to go ahead and say that there none of the proportions could possibly be equal to each other, since there isn't any overlap between any of the confidence intervals. I'm going to add an addendum. There could be an overlap between the US and France, but given that we used a 99% confidence interval, it's not likely. That's all I have for you guys today. I would also highly recommend checking out question number 20 in this section, and then giving that a try and making sure that you know how to use the minimum sample size equation. And then other than that, that's basically all you guys need to know. If you have any questions, just feel free to email me over the break. Last, make sure that you take the test in the testing center on either Friday or Monday after spring break. So that would be the dates that the tests are going to be open is going to be the 25th and the 7th. And so you should have plenty of time to get that done and get your homework finished. So if you have any questions between now and then, just give me Professor Frieden, or oh my gosh, why am I blanking on her name? Our lovely grader, Graciana. Give me Professor Frieden or Graciana a call, and we would be happy to assist you with any questions that you have. I hope you guys have a wonderful spring break and have a great rest of your weekend.